Okay, I've eaten since the last presentation, so let's see how this one's going to go. We're going to talk about complex numbers in exponential form, which is actually a fairly simple idea. Remember that when we're looking at points in the plane, and technically speaking complex numbers are just points in the plane, then those can be also represented with polar coordinates r theta instead of rectangular coordinates x, y. And visually, it's a quite simple geometric idea. Rather than describing the number as the endpoint of this vector, we can also, which is given by xy, we could also take a look at the angle between the vector and the x-axis, and that's typically called theta, and the length of that vector, which is typically called r, and which is, by Pythagoras' law, the square root of x squared plus y squared. And then, well, once we've got all this together, we also see that y is equal to r times sine theta, and x is equal to r cosine theta, and the number z is x plus iy, which can therefore then also be described as r cosine theta plus I sine theta. And so the connection between complex numbers in rectangular form and complex numbers in polar form is that x plus iy is equal to r cosine theta plus ir sine theta, which is r cosine theta plus I sine theta, where the cosine and sine are in parentheses. Okay, the angle theta is also called the argument lowercase arc z of the number, and we'll talk about arguments in just a little bit. And r, well, r is just the absolute value of z as was defined in the previous presentation. Okay, let's take a look at an example. If we're looking for the argument of the number z equals -1 plus root 3i, well, we have to find that angle, and so we realize that because this is x and this is y, y over x would be the tangent of the angle, so the tangent of the angle is -1 over root 3, and that means that theta is, well, the inverse tangent of a negative angle is negative, and then this is 1/2 over root 3 over 2, and sine of pi over 6 is 1/2, and cosine of pi over 6 is root 3 over 2, so this should be negative pi over 6. But then let us also notice that this number is actually in the, well, which quadrant is that? This number is in the second quadrant, right? Because x is negative and root 3 is positive. So that number is in the second quadrant, and the inverse tangent only gives us numbers in the first and fourth quadrants. And, well, from what we remember from polar coordinates is that if the angle is in one of the quadrants that the inverse tangent function doesn't reach, we have to add pi. And then, of course, we also know that if we add multiples of 2 pi, the tangent of theta doesn't change. And, well, now we just add that up and we realize that that is 5 pi over 6 plus 2 pi n. And that really is the argument in lowercase letters of the number z, which means the argument is not unique, and that can't be expected because, after all, any two angles that are 2 pi apart basically look the same unless we specifically count rotations, which we typically don't. Along these lines, then, the unique argument capital theta that is in the interval from -pi open on the left to pi closed on the right, that thing is called the principal argument, which is given a capital letter. We're going to see, as we're working with complex valued functions, that there are certain functions, most notably the argument, the logarithm, and power functions, for which we will encounter this kind of problem. And if the function has a name, typically it'll be in lowercase, and the uppercase letter will give us the principal value of the function, which is typically the standard value that's being reported, even though there are other possibilities. Okay, for multiplication now, we define e to the I theta to be cosine theta plus I sine theta, and well, why would we do that? Because a priori there's nothing that these functions have in common. The reason, however, is that complex multiplication behaves sort of like multiplication of exponentials. Let's consider the product of two complex numbers, z1 times z2. Then that would be r1 e to the I theta 1 times r2 e to the I theta 2 in this polar notation, in this exponential notation. And that is r1 cosine theta 1 plus I sine theta 2 times r2 cosine theta 2 plus I sine theta 2. So, as we have also seen in proofs, if you don't have any better idea, you just go ahead and resolve the definition. And, well, then of course the r1 times r2, we can put that out front, and if we multiply all these cosines and sines, we get cosine theta 1 cosine theta 2, I sine theta 1 times I sine theta 2, which is negative sine theta 1 sine theta 2, plus, and then we get the imaginary parts, cosine theta 1 I sine theta 2, and I sine theta 1 cosine theta 2 right here. Okay, well, if we now use our trigonometry, we realize that cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2, that's cosine theta 1 plus theta 2. And cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2 is sine theta 1 plus theta 2. And that's r1 r2 e to the I theta 1 plus theta 2. And, well, basically that explains why we would choose this to be the notation for cosine theta plus I sine theta. It essentially acts like an exponential with an imaginary exponent. And once we've got the series expansions of the exponential sine and cosine functions, we can show that this is really not just a coincidence in notation if, or once we interpret sine, cosine, and exponential as functions of a complex variable, this identity will in fact work for all complex numbers. Okay, in terms of rules for computation with multiplication, z1 times z2 is, of course, r1 e to the I theta 1, r2 e to the I theta 2, and we've just shown that that's r1, r2 e to the I theta 1 plus theta 2. The quotient z1 over z2 is r1 e to the I theta 1 over r2 e to the I theta 2, and we can expand that with e to the negative I theta 2 in numerator and denominator. Complex fractions really does work just like regular fractions. That can be verified, even though we haven't done so in the previous presentation. Now we realize that this product down here is 1, and so we end up with r1 over r2 e to the I theta 1 plus minus theta 2, and that's of course just the difference here. So you divide complex numbers by dividing the absolute values and subtracting the arguments. 1 over z then is very simple, because that's 1 times e to the I times 0 over r times e to the I theta, and that's 1 over r, just like we did here, and then e to the I 0 minus theta, so e to the negative I theta. Powers, well, powers we're going to revisit with a more formal mechanism, but if you have z to the m, well, that's r times e to the I theta to the m. That's r to the m e to the I theta to the m. And how does that go? Well, that's r to the m e to the I theta to the m minus 1 times e to the I theta, which is r to the m e to the I theta m minus 2 times e to the I theta times e to the I theta, which we know is e to the I 2 theta. And now we just keep splitting e to the I thetas off of the one on the left and sticking them into the one on the right. So we get r to the m e to the I theta to the m minus 3 e to the I 3 theta. And we keep going like that all the way until we get r to the m e to the I theta e to the I m minus 1 theta, which is r to the m e to the I m theta. So again, this complex exponential form works just like a power should do, but again, notice that z to the m isn't equal to this because e to the I theta is a power. Z to the m is equal to this because we can prove it. Z to the negative m then is r e to the I theta to the m to the negative 1. Well, that's r to the m e to the I m theta to the negative 1, and that's just 1 over r to the m e to the negative I m theta by using this law in number 3 here. And, well, we can certainly visualize products and quotients. Let's start with products. We take our complex plane, real parts along the x-axis, imaginary parts along the y-axis. If we then have a complex number with argument theta 1, which is r1 e to the I theta 1, if we have another complex number, argument theta 2, which is r2 e to the I theta 2, then the product has argument theta 1 plus theta 2, and it is r1, r2, e to the I theta 1 plus theta 2. And if we're looking at quotients, well, that would mean we start with a complex number that has an argument theta 1, and that's r1 e to the I theta 1. We want to divide that by a complex number that has argument theta 2, which is z2 r2 e to the I theta 2. And if we do the division, we get an argument that is theta 1 minus theta 2. And the quotient is r1 over r2 e to the I theta 1 minus theta 2, just as we had shown previously. And if we want to look at powers, I'm not going to show the stretch factor, but if I have a complex number with absolute value 1 and argument theta, well, then the powers are just what we get. The second power is you double theta, then you triple theta for the third power, you quadruple theta for the fourth power, and so on, and so on. So powers are something that actually spirals around the origin, but remember, if the absolute value is greater than 1, then these things get longer, and if the absolute value is smaller than 1, these things get shorter. Okay, now the power law, that was one of those where we used what I sometimes refer to as magic 3 dots. And, well, you don't do mathematics with magic 3 dots. So the way to prove these kinds of things that depend on a natural number m is mathematical induction. And so let's see how that goes. We also have a presentation that explains how mathematical induction works. If this is your first exposure to mathematical induction, and then I would just recommend you go ahead and look at the induction presentation either right now or after this one. So, induction always is a base step where you just prove the law for m equals 1, and that's of course quite trivial, right? You stick in 1s and everything's fine here. The induction step is that you assume that the law works for m, and you prove it for m plus 1. And so we just write out the r e to the I theta to the m plus 1, and of course what do you do with a power to the m plus 1? You split off the plus 1 part, and you get r e to the I theta to the m times times e to the I theta, just like we also did a couple of panels ago. Now we can use, because we're allowed to use our induction hypothesis for m, that this is r e to the I theta to the m, that's equal to r to the m e to the I m theta. We still have the r e to the I theta here, but now it's just regular powers, right? We just sort this out. We get r to the m r e to the I m theta plus theta, and that's r to the m plus 1 e to the I m plus 1 theta, which is exactly this law, only with m replaced by m plus 1, and that concludes the induction proof. As an example, well, let's compute 1 plus I to the 19th in rectangular form, that is in x plus iy form. Well, if you wanted to multiply that out with the binomial theorem, well, I can't stop you because I'm not even in the same room with you, but I would recommend you don't do that because that is no fun at all. When you've got a large power to compute, of course, the exponential form ought to be the way to go. And so if I have 1 plus I to the 19th, well, that has absolute value root 2, and it has argument pi over 4 because it sticks out exactly along the diagonal. Now raising this thing to the 19th is not a problem. That's 2 to the 19 halves e to the I 19 pi over 4, and of course 19 pi over 4 we'd like to have an angle between negative pi and pi, so that becomes 2 to the 19 over 2 e to the 3 pi over 4. And well, that's, if we want to now get back to rectangular form, that's 2 to the 9th times 2 to the 1/2. We'll see that that thing will cancel, times cosine 3 pi over 4 plus I sine 3 pi over 4. And well, now we have to figure out what the cosine and the sine of 3 pi over 4 is. Let's see. The cosine is negative, and it's 1 over root 2. So negative 1 over root 2 plus I over root 2 should be what we get back here. 2 to the 9th, 2 to the 1/2. Negative 1 over root 2 plus I times 1 over root 2, and now the 2 to the 1/2 cancels. And we end up with the result being negative 2 to the 9th plus I times 2 to the 9th. That is a lot quicker than any attempt to multiply out these parentheses. And, well, if you just have a product of two numbers, then we typically use the form in which the numbers are given, because transforming from one form to the other takes more work than just multiplying the numbers either in exponential form or in rectangular form. Yeah. Okay, now we want to talk a little bit more about arguments, and if you look at the lowercase argument of two numbers z1, z2, well, that is the argument of r1 e to the I theta 1 plus n1 2 pi. Remember that the lowercase argument is only unique up to an additional multiple of 2 pi. And similarly, z2 is r2 e to the I theta 2 plus n2 times 2 pi. And if we multiply that together, we get that's the argument of r1 r2 e to the I theta 1 plus theta 2 plus n1 plus n2 quantity times 2 pi, which is just theta 1 plus theta 2 plus parentheses n1 plus n2 parentheses closes times 2 pi. And if we now break that back up, that's theta 1 plus n1 2 pi plus theta 2 times n2 2 pi, which is the argument of z1 plus the argument of z2, which is of course nice. These kinds of laws are easier to remember. It's sort of like a logarithm law, but we need to be careful. This only works for the lowercase argument, for the one that doesn't have unique values, and this example I think is going to show that to us. For the numbers z1 equals negative root 3 minus I and z2 being 1 minus I, we want to find the argument of z1, z2 lowercase, as well as the principal value of the argument. So let's see, z1 is negative root 3 minus I, so that would be y over x, so that would be tangent inverse of 1 over root 3, which was pi over 6, and this thing is in the fourth quadrant, so it's negative pi over 6. Hang on, okay, well, the magnitude being 2, yeah, that's 3 plus 1, that's not a problem. And this thing is, I keep thinking that ought to be negative pi over 6. Give me a second here. Okay, I'm back. My mistake was that negative root 3 minus I is not in the fourth quadrant, it's in the third quadrant, and that means we have to get our pi over 6 and then subtract pi in order to stay between negative pi, and so that means that really is 2 times e to the negative I, 5 pi over 6. Sorry about the confusion there. z2 is 1 minus I, which is a whole lot easier. That one actually is in the fourth quadrant. The magnitude is root 2, and the angle is negative pi over 4. And so then the argument of z1 plus times z2 would be negative 5 pi over 6 plus negative 5 pi over 4 plus the multiple of 2 pi that's always there. Now if we add those together, the common denominator is 12. So we get negative 10 over 12 minus 3 over 12, which is negative 13 pi over 12 then, plus the 2 pi k. And it's always customary to push this number back between negative pi and pi. So if we add 2 pi here, we get 11 pi over 12 plus 2 pi k. And that's the lowercase argument, which is equal to the sum of the lowercase arguments that we would have had otherwise, because that's where these guys just have the plus 2 pi k, and then the adjustment here just doesn't give us anything different. It's the same family of values. But the principal value of the argument, the value that has to be between negative pi and pi, is 11 pi over 12, and that is not equal to the principal argument of z1 plus the principal argument of z2, because that would really be the negative 13 pi over 12 that we computed here, because this one and this one are the principal values of the argument. So we need to be careful when we work with arguments. If we really are looking at principal values of the argument, then certain laws that we would like to have actually have to be taken care of a bit more carefully than if we go with the lowercase argument, which has the multiple values. Okay, now let's talk about roots. If you've got two complex numbers, r1 e to the I theta 1 and r2 e to the I theta 2, they're equal if and only if, well, first of all, they both must have the same length, so we must have that r1 is equal to r2, and once we've got that, they also must have the same arguments, and that means that the arguments, these values theta 1 and theta 2 that are being reported, can only differ by an integer multiple of 2 pi. Well, that means if I now look at z to the n equals to z0, that's r to the n e to the I n theta equals r0 e to the I theta 0, which gives us that r to the n is r0 and n times theta is theta 0 plus k times 2 pi, which means that r will be the nth root of r0 and theta will be theta 0 plus k times 2 pi divided by n. And we can of course separate those fractions out to keep this part here separate, which gives us multiple values. And that means that the nth roots of the complex number z0 are ck being nth root of r0 times e to the I theta 0 over n plus k times 2 pi over n, where really all the information that we need is in the theta 0 over n, because whenever you have an nth root, you can always add k times 2 pi over n to the argument and get just yet another nth root of that number. And k goes from 0 to n minus 1 there. Okay, as an example, we want to compute all nth roots of unity, that is, we want to compute all nth roots of the complex number z equals 1. Well, z is 1, which is 1 times e to the I 0, so that means r0 is 1 and theta 0 is 0. And that means the roots are ck being e to the I k times 2 pi over n, where k goes from 0 to n minus 1. Now we can visualize that for, say, n equals 12. We take our complex plane and we draw a unit circle. And now here's a 1, and that would be the e to the I 0 times 2 pi over n. Then we realize 2 pi over 12, well, that's pi over 6, so the first root of unity sticks out in this direction. And now all the other ones are just adding pi over 6 in the argument, so you get how many roots of unity? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 roots of unity, and this is now the analog, the complex numbers analog of what we had learned a long time ago, that a linear equation has one solution, a quadratic equation has two solutions. Well, an nth order equation has n solutions. The easiest nth order equation is z to the n equals 1, and that thing has 12 solutions. And we've got all those solutions because now we've got that second dimension for the complex numbers, which allows us to rotate these arguments all the way around the origin, so we don't just get two real solutions as we would get if we solved this equation in the real numbers. Okay, another example. Let's actually concretely compute the fourth roots of 1 plus root 3i. And 1 plus root 3i, that's 2e to the I pi over 3. Well, why is that? Okay, the magnitude or the modulus is 3 plus 1 square root of 4 is 2, yes. It's in the first quadrant, so the angle should be in the first quadrant, no problem there. And the tangent is root 3 over 2, and that would be the tangent is root 3, so that's root 3 over 2 divided by 1/2, and the sine of pi over 3 is root 3 over 2, yeah, so that is e to the I pi over 3. And the roots of this thing now are e to the I pi over 12 plus k times pi over 2, 2 pi over 4, right? And that is 2 times cosine pi over 12 plus k pi over 2 plus 2i sine pi over 12 plus k times pi over 2. And here's where we need trigonometry, because we'll ultimately need the cosine of pi over 12 and the sine of pi over 12. So let's use some half angle identities. Cosine pi over 12 is cosine 1/2 times pi over 6, which is the square root of 1 plus cosine pi over 6 over 2. Look up your half angle identities if you don't remember them, and I wouldn't blame you if you don't remember them, because I don't necessarily have those memorized either. But cosine of pi over 6 is 1/2 root 3, right? So we get a 1/2 root 3 here. Find a common denominator, so that's square root 2 plus root 3 over 4, which is square root of 2 plus square root of 3 inside the big square root divided by 2. And the sine pi over 12 is a sine of 1/2 pi over 6, and that's the same half angle identity, only that the plus is replaced with a minus, And so then we get a very similar computation. We get the square root of 1 minus 1/2 root 3 divided by 2, which is the square root of 2 minus root 3 divided by 4, and then of course we'll pull that out and get square root of quantity 2 minus root 3, quantity closes, divided by 2. Once we've got that, we can get back to those fourth roots, and this is what they are. And so now the first or the 0th fourth root, and I index with the k here, that would be cosine 2 cosine pi over 12 plus 2i sine pi over 12, and so that's square root of 2 plus root 3 plus I times square root of 2 minus root 3. And the other ones now, well, because we have a pi over 2, what happens is that we just get a quarter turn rotation for all the other roots, right? And if you take a number and rotate it a quarter turn, basically what happens is the number is in the same position in the next quadrant, only what used to be the x-axis is now the y-axis, and what used to be the y-axis is the negative x-axis, which means the y becomes the negative x value and the x value becomes the y value, and we can now push that through for all the other ones to get y value becomes negative x value becomes the y value, and finally y value becomes negative x value becomes the y value, and these are the four fourth roots of 1 plus root 3i. If that last geometric statement that I gave you doesn't make sense, go ahead and draw it and realize that a quarter rotation just does this interchange that I mentioned. And with that, we're not done with the complex numbers in exponential form. We will use them frequently in what follows, but at least we are done with the introduction. Thank you very much.